Welcome to the Probability and Statistics course. Today we are going to talk about random variables. We are going to see especially the discrete random variables and also what the probability distribution function is. Here we have our sample space, as we have seen using Venn diagrams, the event and event A, and now we are going to define the random variable. It will be a function that takes every element of the sample space, each element of the sample space, and sends it to a real number. Now, the random variable should have an important property that for each interval of real numbers, the set of elements in the sample space which are taken into this interval is an event. The definition of the random variable is that a random variable x is a function from the sample space S to the real numbers R, such that the preimage of every interval is an event of S. Now, if x takes discrete values, then it is called discrete random variable. Otherwise, it is called continuous random variable. What do we mean by that? We are going to write that we mean that x takes values in a discrete set that means, for example, that the random variable will take values, for example, in the set 1, 2, 3, and so on, or takes values 0, 1, and so on. That's the discrete random variable. And for this lesson, we are going to work with discrete random variables. In the next lesson, we are going to see what a continuous random variable is. Now we are going to work through an example and try to understand the notion of the discrete random variable. We have that we perform the experiment of repeatedly tossing a coin and assume that a head appears. If a head appears, then we win $1. On the other hand, if a tail appears, we lose $1. And we are interested in finding what is the probability that we win on the first toss. That we win $1 on the first toss. In this example, we have that the sample space is head or tail. When we toss the coin, we can observe a head or a tail. And for us, it means that if we observe a head, we win $1. If we observe a tail, we lose $1. Now, the random variable, we defined it for this experiment as it sends the head to the number 1. As we said, it's going to take every element of our sample space and send it to a number, a real number, and tail to number -1. The numbers we have used here, it can be different. It doesn't have to be 1 or -1. The reason I used 1 and -1 is that it makes sense for this example, because when we bring a head, we win $1, we put 1. If we bring a tail, we lose $1, we put -1. It is important, though, that whenever head occurs, we mean that from here x will be 1, and otherwise x is -1. We see here that the random variable x takes discrete values, so it is a discrete random variable. And to talk about probabilities, the probability, our question was the probability of winning $1. $1, we need to look at this to see which element in our sample space gets sent to 1 by x. In this case, we know that it's the element head. As we wanted it to be, we wanted the element head to correspond to winning. And hence, the probability of x equals 1 equals, as defined here, the probability of this, which is the probability of observing a head, which for our case is half. Now let's do our example a bit more complicated. So suppose we toss the coin 2 times now to times. Our sample space in this case is, we observe two heads, a head and a tail, tail and a head, or two tails. And so we define our random variable. It takes the element two heads, and we'll take it when we bring two heads, we win twice, so we have won $2. So we're going to write here that this is sent to 2. It also will take this element and this element, which means that we have won one time, and it means we have won $1 one time, we lost the other time, so actually we haven't won anything. So this will be sent, these two elements will be sent to 0. And the element tail, tail, which means that we lost both times, we lost $2, is sent to -2. Now, if we ask the question, what is the probability of winning? Of winning both times, so we'll put here of winning $2. We want to find the probability of x equals 2. So we want to find the probability of this, the probability of actually having observed two heads, one head in the first row, one head in the other row. And in this case, this probability is 1/4. Let's see graphically now how this example, we can work this example using random variables. So we toss the coin. We said that we toss the coin once in this case. We observe a head or a tail. Now we send through the random variable the head to 0. Here it's a bit different than the example we worked. We haven't used the same numbers, but as we said, it doesn't matter really to which numbers the random variable sends the elements. So in this case, h is sent to 0 and t is sent to 1. So x of h here will be 0, x of t is 1, and the element, the number 0 is sent back through x to an event in the sample space, as well as number 1 is sent back to an event in the sample space. The probability distribution function of a discrete random variable will be the function that calculates the probability that x will be equal to a number. And that should be defined for every x in R, every real number. Let's see an example. First of all, let's see the properties of the probability distribution function. It is greater than or equal to 0 for every x in R. This we should expect as it is a probability, and we know that the probability should be greater or equal than 0. Also, if for all x that the probability is of the random variable taking the value x is greater than 0, if we sum up all these, the summation should be equal to 1. Let's see an example to understand this, how it works. And here is the example of the 2 dice. We throw 2 dice. We have our sample space. As we know, 36 elements in our sample space. And the random variable x here we define will be the sum of the 2 dice. So each element from this table is going to be sent to a real number. Element, as this is the sum of the 2 dice, the element 1, 1, it will be 2. It's sent through the random variable x to 2. So here, these elements, 2 plus 1, 3, can be sent to the real number 3. Also, the numbers here, 3, 1, 2, 2, and 3, 1, the sum is 4, so they are sent to 4. The same way, these elements all here, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. The sum is 7, they are sent to 7. We do the same way with all other elements up to the last one, 6 plus 6 is sent to 12. Now we have here, we create this table which we have entered the real numbers that are random variable, the values that are the random variable can take, because for any other value that our random variable can take, the probability will be 0. We just say that f of x will be 0 for all other x. We cannot include everything in the table. For all other values, 2 up to 12, we calculate the probabilities. For example, if we take the case that the random variable is 5, takes the value 5, we can say that that is the same as the probability of observing a 1 in the first die and a 4 in the second, 4 in the first, 1 in the second, 2 in the first, 3 in the second, 3 in the first, 2 in the second. That's 4 out of 36. We remember here that 1, 4 is different than 4, 1, as our dice are colored. It's red and green, and so it's different to observe a red 1 and a green 4 than a red 4 and a green 1. Also, here, for example, that probability that the random variable takes the value 2 will be the probability that we observe the element 1, 1, which is 1 out of 36. As we have seen, f of x should have the property that is greater or equal than 0. It is a probability, and of course we can see that for values 2, when the random variable takes values 2 up to 12, f of x is greater than 0. For all other x in R, we said that f of x will be 0. And also, the second property, we said that if we sum up all these probabilities that are not 0, they should add up to 1. So you can see, if we add up all these numbers, they actually equal to 1. When we talk about the probability distribution function, it is nice to make a picture to see how we can visualize the probability distribution function. The most common way to visualize the probability distribution function is this. We have here the values, the possible values that the random variable can take, the ones that the probabilities are not 0. We put them in this axis, in x-axis, and then we draw bars that their height goes up to the value that f of x is. So, for the first here, for if x takes the value 2, we know that this should correspond to the value 1 over 16. The same way for the other bars, and we can see in this case we have created a symmetrical picture. Now we are going to work through an example to see analytically how we calculate all this. Another example, we assume that x is a variable. In this case, that counts the number of heads when we toss a coin 4 times. A fair coin four times. So x will be the number of heads in 4 tosses of a coin. Each time we have an experiment, we need to know, to make clear what we are interested in, so we can define our random variable properly. So we know that a coin has no memory. That means that each time we throw a coin, there is no memory. It doesn't matter what we brought before. So that means the tosses are independent. Having brought a tail, it doesn't mean that there is more probability or more chance or less chance to bring a tail on another throw. So for this example, we write down all possible outcomes, our sample space. We have 4 throws, so we have the following possible outcomes: 4 tails, like before we denote by T the tails and by H the head. Now I group the outcomes depending on how many heads we have observed. Here, head, tail, tail, head, tail, tail, tail. It's going to be useful when we define the random variable. Here we have tail, tail, head, head. We have to be careful not to forget any outcome. Using counting techniques, we can actually know beforehand how many outcomes we expect to have, so we don't forget anything. I'll write it here. Also, we have observed 3 heads and a tail. And finally, 4 heads. We have written down all possible outcomes, and now we can define the random variable x, so that we remember we'll put numbers that make sense to us. As we are interested in the number of heads, we'll put 0 for these. We have no heads. We are going to put 1 here, that we have 1 head. 2 for these outcomes, as we have 2 heads. 3 for these outcomes, and 4 for this outcome. So what we actually mean here is that, for example, x of h t will be, it's in this group, will be 3. So we have that the probability of h t t h, the probability of observing 2 tails, we are going to use the multiplication rule. We can do that because we said that each outcome here is independent from the other. So we know that each one has half probability of being observed. So in this case, half for head, half for tail, again half for tail, and half for head. And this is 1/16. Now we are going to calculate the probability distribution function for x equals 0, 1, 2, 3, and 4. We know for all other values, f of x will be 0. For every, this is the simple, we mean for every x and r that is not equal to these values. For these values, we are going to calculate f of x one by one. So the probability of x equals 0 will be equal. We bring back what we have written here before. It's one outcome out of total 16. If we count here, we have a total of 16. And so the probability of x equals 0 is 1 over 16. The same way, the probability of x equals 1 will be, we see we have 4 points here, 4 outcomes, so 4 out of 16. The same way, we can calculate the probability of x equals 2, which is 6 out of 16. The probability of x equals 3, which will be 4 out of 16. The probability of x equals 4, the last one, which is 1 over 16. The properties here, we see that, of course, these all are probabilities, so this will be f of 1, f of 2, f of 0, this one, f of 1 here, f of 2 here, f of 3 here, f of 4 here. This is a typing mistake, should read x equals 4. These all probabilities are greater than 0, including this, which for all other numbers, real numbers, is 0. We have that the first property will be true. And the second property, all these probabilities should sum up to 1. We see here that the sum of f of x for all x is actually 1 plus 4, 5, 11, 15, 16 out of 16 is 1. When we have discrete examples like this, it would be nice to make a nice table to include all the information. So we usually have x in the first line and f of x the second line. For this case, we include all the probabilities that are greater than 0. That's for 0, 1, 2, 3, and 4. So we know that this is 1 over 16. This is 4 out of 16. This is 6 out of 16. Here, 4 out of 16, and 1 out of 16. And finally, we're going to do a graph of the probability distribution function. We said that we are going to put on X the points that the probability is greater than 0. So we're going to put 0, 1, 2, 3, and 4. And we draw bars up to this number. So I put on the y-axis 1/16, 2/16, 3/16, 4, 5, and 6. And we have for 0, we draw the bar. For 1, we draw the bar here. For 2, again. For 3, here. And for 4, again. And we can see here that actually, in this case, again, for this experiment, the picture we get is symmetrical, but this is not the case for any experiment we have. So we are going to see what we have seen today. We have talked about random variables and see several examples to understand the notion of the random variable. In particular, we saw what a discrete random variable is, and we've seen the probability distribution function. For more information on this lesson, you can visit the web page of UNINETTUNO MedNet U project.